On va reprendre donc en mode plutôt visio l'ensemble de nos interventions séminaires de SystemX à partir du mois de septembre. Donc la première est aujourd'hui. Je profite déjà tout de suite avant de présenter un peu plus avant Thomas Bonald, qu'on a un autre séminaire en octobre, le 22 octobre, par Kamel Medjaher sur des sujets pronostiques et health monitoring. Sur le site web, il y a déjà l'annonce, donc vous pouvez aller regarder sur le site web de l'URT. Et pour revenir à l'événement qui nous rejoint, enfin qui nous réunit aujourd'hui, je vais introduire un petit peu Thomas. Thomas est un chercheur professeur à Télécom Paris, donc à l'Institut Polytechnique de Paris, et puis il dirige en particulier au LTCI, le laboratoire de Télécom Paris. Il dirige l'équipe DIG pour Data, Intelligence et Graph. Voilà. Et ses travaux concernent justement l'analyse des graphes, également aussi des sujets autour des séries temporelles et puis du langage naturel. Bon, je ne vais pas faire son panégyrique, mais il a beaucoup de publications et de brevets à son actif. Et il a en particulier quelque chose dont il va nous parler, je pense, dans la deuxième partie de sa présentation, une contribution à l'environnement scikit-learn, mais enfin scikit-network exactement s'appelle l'outil, la plateforme qui rapatrie un certain nombre d'algorithmes autour des graphes. Il a eu aussi des distinctions, une médaille Bonald en particulier en 2013. Et puis là, l'IP Paris s'est beaucoup structuré l'année dernière et dans cet exercice d'organisation, il y a une école doctorale qui est née, il y a une école doctorale multidisciplinaire qui s'appelle l'école doctorale IP Paris, dans laquelle justement Thomas assure la co-responsabilité du domaine informatique, données et IA. Voilà, j'ai fait un petit peu la présentation de Thomas. Je vais le laisser peut-être aller un peu plus avant sur à la fois son sujet, sur les méthodes spectrales pour les graphes, et puis s'il veut en dire un peu plus, qu'il n'hésite pas. Je te passe la parole, Thomas. Avant juste que tu prennes la parole, juste je voulais dire à toutes les personnes connectées, je suis content parce que je vois qu'on a quand même plus de 40 participants et ça va peut-être encore augmenter. Comme il y a beaucoup de monde, si vous souhaitez intervenir dans le cours de la présentation, vous levez la main, il y a une possibilité de lever la main. Et bon voilà, Thomas pourra vous la passer. Et puis de toute façon, on aura éventuellement à la fin de son échange, de sa présentation, une possibilité d'échange et de discussion pendant un quart d'heure. Thomas, je te passe la parole.
Eh ben, merci beaucoup, Patrice, pour l'introduction. Merci pour cette invitation. Et donc, je vais donc vous présenter ce qui m'occupe quand même beaucoup en ce moment. Alors, avant de commencer, donc, je ne sais pas si tout le monde est francophone. So, if you'd like the talk to be in English, please raise the hand. Otherwise, we'll stay.
Les slides sont en anglais, hein, sinon, je crois. Hein.
Donc, je vais continuer en français, si ça vous va. Donc, effectivement, je vais vous parler de méthodes spectrales pour la représentation, l'embedding de graphes, et donc, en particulier d'un logiciel, enfin une bibliothèque Python qu'on développe avec Nathan Delara et Quentin Allus, qui sont deux de mes doctorants. Voilà, et donc, pourquoi je ne peux pas passer là, mais c'est transparent. Voilà. Voilà, donc on va parler de graphes. Et donc, des graphes, il y en a plein autour de nous. Alors, il y a des graphes un peu très visibles, comme les réseaux sociaux, par exemple. On a aussi, peut-être un peu moins visible, le graphe du web ou de Wikipédia, ce genre de choses. Donc, les liens entre les pages qui constituent le web. Et puis, on a peut-être encore un peu moins visible, par exemple, les graphes de connaissances, comme Wikidata, qui permettent de structurer les connaissances et qui sont par ailleurs des objets très étudiés dans l'équipe. Et puis, donc ça, c'est toute une famille de graphes. Puis, il y a aussi toute la famille, on peut dire, des graphes bipartis, où on a des nœuds de types différents, par exemple un graphe entre utilisateurs et produits, quels produits ont acheté les utilisateurs, dans quel film ont joué les acteurs, quelles lois ont voté les députés, quels mots on utilise dans le document, etc. Quels médicaments ont pris les patients. Et donc ça, c'est des graphes très intéressants et qu'on trouve un peu partout et donc qui sont une source extrêmement riche d'informations. Donc on va essayer d'analyser un peu tout ça, et le point commun de tous ces graphes, c'est qu'on peut les représenter par des matrices. Donc soit des matrices carrées pour des graphes usuels, on va trouver typiquement un 1 en entrée IJ si j'ai un lien de I à J, du nœud I vers le nœud J, et cette matrice sera symétrique si le graphe n'a pas de non dirigé. Et puis pour les graphes bipartis, on aura plutôt une matrice qu'on appelle une matrice de biadjacence. Ce serait une matrice rectangulaire. Là, par exemple, les lignes vont correspondre aux utilisateurs et les colonnes vont correspondre à des produits. Donc, il y a des nœuds de nature différente. Et on va essayer de traiter ça dans un même cas, plus ou moins. Alors, un point commun de tous ces graphes, et tous ces graphes, les vrais graphes, les vraies données, c'est que ça correspond à des données qui sont extrêmement éparses. Donc, ça correspond à des matrices creuses, les matrices creuses. Vous avez dans la dernière colonne, que ce soit pour les graphes duels ou les graphes bipartis, sur des datasets standards, la densité de ces matrices, c'est-à-dire la fraction des entrées non nulles par rapport à l'ensemble des entrées de la matrice. Et donc, on est très couramment dans des ordres de grandeur de 10-5 à 10-7, c'est-à-dire qu'on a essentiellement que des zéros dans cette matrice, et donc ça demande évidemment un traitement bien particulier de ces objets. Et donc, on peut se poser plein de questions quant à l'analyse de ces graphes. On voudrait, par exemple, en comprendre la structure, c'est-à-dire savoir s'il y a des groupes. Alors, je vois qu'il y a quelque chose sur le chat. J'espère que je n'ai pas raté quelque chose. OK, Johannes would like in English. So, Johannes, so maybe we can switch to English. Sorry, I haven't seen your... So if that's okay for everyone, I will switch to English for Johannes. Are you here, Johannes? Okay, so maybe I will switch to English. Yeah, okay. No, but I mean, maybe someone else would like it to be in English, I don't know. That's fine. I mean, that's what we do in Telecom Paris. If there is at least one student who like the class to be in English, we switch to English. So there are many tasks you'd like to. Many type of tasks you may think about when you like to analyze graph, like clustering. So how to find relevant groups of nodes in this graph. So-called communities or clusters. You may like to have possibly the hierarchy of the graphs of the nodes, if any. You may like to round these nodes to find the most interesting nodes, or to classify the nodes. If you have, let's say, some labels for some of the nodes, you'd like to find the labels of the other nodes, for instance. Or you like maybe you want to embed the graph in some low-dimensional space, and we'll essentially talk about that later. And the common point here is that we like to be able to analyze a huge graph, like with millions of nodes, so you need to have methods that are scalable, because many real graphs are very, very large. And this is the outline of my talk. So I will first talk about this topic of graph embedding, and especially we'll talk about the spectral method for that. And in the second part, I would like to spend some time to show you scikit-network, which is the Python package that we developed with Nathan, Quentin, and others. We'll give an overview and a brief demo of what you can do with this package. So, of course, if you'd like to ask questions, please feel free to raise the hand. Okay, so first, graph embedding. So the idea is to represent all the nodes of the graph as vectors in some low-dimensional space. And so the first obvious motivation is to reduce dimension so that maybe you can apply usual tools like if you think of scikit-learn, for instance, most of the algorithm only work for dense metrics, and you cannot represent a graph as a dense metric. It's too big. And maybe a more deep reason why you like to reduce dimension is a curse of dimensionality. The fact that in a very high dimensional space, which is what you have when you have your raw data, which is a huge matrix, so with a large number of dimensions, is to find a space where you can represent data so that the distances in this space are relevant, and it's often called metric learning. So how to find representation so that two nodes that are close in the graph, meaning that maybe they are connected or there are many paths between them of low length. You like these close nodes in the graph to be also close in their representation, in their embedding space, in terms of the Euclidean distance. Okay, so that it's very easy to, for instance, apply k-means or predict new links or detect anomalies, and you can apply a usual tool for that. Okay, but it's obvious not. I mean, it's not obvious how to do this compression, how to represent this graph. So each node of the graph as a vector of low dimension. So there are many techniques, and the most popular are spectral methods. So we see that they consist essentially in the spectral decomposition of the Laplacian matrix. I will introduce that in details. So just to mention that the two papers I mentioned here have each of them has more than 8,000 citations. So these are very, very popular methods. There are other techniques. I won't describe them, but some are based on the random walls, like not2vec, which is inspired by word2vec, for those who know. So word2vec is a common tool to vectorize words. Okay, but the techniques are similar. And there are also all these techniques based on neural nets, like with many types of neural nets that are typically a bit, more, computationally expensive, but that may give a relevant result, especially if you have metadata that you like to incorporate in your graph. So, but today I will really focus on the spectral method. And so the spectral method basically are based on this notion of Laplacian, and the Laplacian is just, so I will first focus on a regular graph undirected, represented by its adjacency matrix A. And the Laplacian matrix is just G minus A, where D is a diagonal matrix of the grid. And it's related to the heat equation, so to the physics. And actually, it's a way to describe how heat flows in a graph, which is a discrete object, whereas in physics, usually you have a continuous systems. And so you have this equivalent of the heat equation, heat diffusion, that works with that involves the Laplacian matrix. Here, T is a vector of temperature of all the nodes, and you see, you assume that heat flows only through the edges of this graph. Okay, and you can observe how how the system evolves through this equation. There is another very interesting interpretation of this Laplacian matrix in terms of a mechanical system. You may see the nodes of the graph as particles, and the edges are springs, are attractive springs. Okay, so that two nodes that are neighbors tend to be attracted by this spring. And you can do this very nice exercise. You put the nodes on a line, at some positions like x1, xn. So there are n nodes here. So this is, for instance, one on the right. You have one possible location of these nodes. And the question is, what is a good way to put this node on the line? So in physics, usually you think about energy, and you can very easily compute the corresponding potential energy of such a position, such a state. And as you know, the potential energy induced by a spring is proportional to the stiffness of this spring and the square of the distance between the two particles. And so you get, if you sum over all these edges, so you sum over all positive entries of the matrix, you get this expression of the potential energy, and you can easily, very nicely express it through the Laplacian matrix in vectorial form. So it's X transpose LX. Okay. So again, you have a strong connection with physics. So this is a static system, but you may introduce some dynamics. And essentially, what you can do is to release. So you start from some state, and you release the system. Okay, you let it evolve, and then you can write the law of physics, so the Newton's second law of motion. And again, you can express it through the Laplacian. It's very nice, very simple. And you can look at the periodic behavior, and you see the system as a harmonic oscillator. And you can see that the eigenmodes of this system, so leading to a periodic behavior, are just the eigenvectors of the Laplacian. And the eigenvalues, the corresponding eigenvalues, are the levels of energy. They're also the square of the eigenfrequency of these periodic behaviors. Okay. And so I mentioned this because this is really related, directly related to the problem of graph embedding. But to see the link, let's start with an optimization problem. So again, you have your graph, you have n nodes, and assume you'd like to represent each of these n nodes through a vector in dimension k. Okay. And you want to do that so that two nodes that are connected are close in the embedding space, basically. So it's very natural to introduce this problem as an optimization problem. You'd like to find x that minimize the sum of the square root of the distances over all edges, okay, which is exactly what is written here. So the cost here is the sum of the square distance between neighbors, basically. So of course, this optimization problem alone is not well defined, because the solution would be to put all nodes at the same location, so the distance would be 0 for everyone. So you have to introduce some constraint, and a natural constraint is to let your embedding to be centered. So on average, you'd like location to be in 0, and to have a unit covariance. So if you select one of these nodes at random, its expected position is in 0, and the covariance matrix is the identity. And so if you do that, you have a very, well posed problem. And it can be expressed through a trace problem involving the Laplacian matrix. It's quite easy to see, if you remember what I said about this potential energy, because since the square root of between these two vectors is the sum of the square of on each component. And so basically what you will see that you'll see each component of each dimension of your embedding space as a system where you'd like to look at the associated potential energy, and you'd like just to minimize the potential energy of each component, which is the corresponding trace problem. Okay, so that's a problem you'd like to solve. and you may not be surprised that the solution involved the spectral decomposition of the Laplacian. Okay, so more specifically, the minimum is given by the first eigenvectors of the Laplacian, which is written in compact form here. And so the physical interpretation is again that if you look at each dimension, so each component of your embedding, then you will find the first eigenvectors of the first eigenvectors of the Laplacian that correspond to eigenmodes, and the eigenvalues correspond to the levels of energy. And of course, the lower the energy, the better the representation, and I mean the state in terms of physics, because I mean, you know that the nature wants always to minimize energy, and indeed you will find the most interesting information in the lowest level of energy. And interesting question is where you should stop. I mean, which dimension you should choose for your embedding space, and you can do that by looking at the spectrum of the Laplacian. It turns out that there is another very interesting metric that you may use, and we'll see a bit later that actually it gives a better result. I must mention that it's also related to a kind of normalization of the Laplacian called the normalized Laplacian, for those who know. But let's take this matrix is the transition matrix of the random walk. Okay, so if you you imagine you have someone walking in the graph, you choose one of the outgoing edge uniformly at random. Then you define a Markov chain, and this Markov chain has a transition matrix P, where Pig the probability that you move to J when you are in node I. Okay, and so it's really just normalization, left normalization of the adjacency matrix by the diagonal matrix of the degrees. So it's a stochastic matrix, and interestingly, it's also related to the problem of heat diffusion, like the Laplacian, but now it's a discrete time diffusion. Imagine that at each time step, you let heat flow through the edges, so that your temperature at time t+1 will be the average of the temperature of your neighbors at time t, which is what is written here. Okay. Now, you have also a harmonic oscillator associated to this transition matrix. And the key difference with the previous one is that now you will add masses to the particle. Previously, I assumed that all particles have the same mass, which is 1. Now I will take for each particle as it matters the degree in the graph. Okay, so that basically nodes of high degree will have a higher inertia in the system, and so we can, in a sense, will have a stronger impact on the resulting eigenmodes on the state of the system. And these are exactly the same equations as before, except that you have to multiply on left by the mass according to Newton's second law of motion, which is here the diagonal matrix of the degree. Sorry, this should be a di. Sorry, this is a typo. It should be di, so the mass of degree I. And here it's indeed the diagonal matrix of the degree. And so, again, if you look at the eigenmodes of this oscillator, you will find the eigenvectors of P now, of the transition matrix of this random walk. And levels of energy are now 1 minus the eigenvalues of P. Remember that P is a stochastic matrix, so its spectrum is between -1 and 1. And so the lowest levels of energy corresponds to the top eigenvectors of the transition matrix, thus having an eigenvalue close to 1. And if you come back to the optimization problem, it's exactly the same type of problem, but now again, you account for the degree of each node. And so the first condition on the fact that you'd like the embedding to be centered, it is exactly the same, but you weight each node by its degree. Okay, and the same for the condition on the covariance matrix. So essentially, what you will do is that you assume that if you sample one of these nodes, not uniformly, but in proportion to its degree, then on average, you have something that is centered and with a unique covariance. Okay. So now we again, you give more importance to nodes having high degree, and so it's equivalent to sample the edges of this network instead of the nodes. Okay, if you sample one of these edges uniformly at random, and you take one of the corresponding nodes, is exactly as if you had sampled the node in proportion to their degrees. And we'll see later in the experiment that this has a strong impact on the result, and usually it gives a better embedding. And so the corresponding spectral embedding is, so you have to solve this truss problem. You just have modified the constraints. And the solution is given by the eigenvectors of this transition matrix. Okay, and so again, the eigenmodes, the eigenvectors corresponding to the top k dimension of your embedding are the eigenvectors of the transition matrix, and this corresponds to the eigenmodes of the first eigenmodes of this harmonic oscillator. Okay. And again, you're interested in those having the lowest level of energy, and they are very different from what you have when you don't account for the weights, for the masses of these particles. An interesting property of this embedding that you don't have with the Laplacian matrix is that each node will be located up to some scaling at the barycenter of its neighbors. And actually, it's very easy to see if you come back to the spectral, the definition of this embedding, which are eigenvectors of this transition matrix. So you can write them differently. So it's written in blue here. And if you forget about the right-hand factor, which is a scaling, you find that x is equal to px, and px is just the vector of the set of vectors of the barycenters of each node. So if you take row I of this matrix px, you will find the average of the vectors of the neighbors of node I. So let's say node I, these red nodes, you will look at all these neighbors, so nodes j, and you'll take the average of their location in the embedding space, and this will give you up to the scaling, the embedding of node I, which is a quite interesting property that you may exploit in practice. And you don't have this with the usual Laplacian embedding. There are many variants that you may apply to this embedding, and actually this is what I insisted on that in the abstract of my talk. And indeed, you will see in the experiment that this make a strong difference on the result. The first one is that you may apply before doing the spectral embedding a form of regularization, which consists in adding a constant to all pairs of nodes. So it's as if you add an edge between all pairs of nodes in the networks with some parameter gamma. Or it may be in proportion to the degrees. Okay, you can do that in two ways. So d here, the vector of the degrees. And it exactly corresponds to, it's equivalent to the regularization of the optimization problem. And you can prove that it makes the system much more robust, and in particular to noise in particular. For instance, if you have isolated nodes, this may have an impact on the embedding if you don't apply regularization. Their impact vanish if you apply regularization. This is something we've shown with Nathan Delara quite recently on a block model. We have shown that if you take the top dimension of your embedding with regularization, this allows you to identify the largest clusters of nodes if you do if you're interested in clustering. So this is the first important pre-processing you may do. There are other things you may do which are more post-processing, and the first one is the scaling. So you may scale your embedding, so each component of your embedding, by some power of the eigenvector, either of the corresponding eigenvalue. And if you think that lambda, if you remember that lambdas, the eigenvalues correspond to levels of energy, you may play with that. And so in particular, you can show that if you have alpha equal to 1/2, then this will equalize the levels of energy of this, because you will apply some scaling now on each component, and this will equalize the levels of energy of all these components of your embedding, which is not the case in the original embedding, just because you have imposed that the covariance matrix is the identity, so that you have essentially the same variance on each of the components, which means that the last eigenvectors you consider, the last component, will correspond to higher levels of energy. And the final, another very important post-processing is the normalization. So you would just make them all vectors live on the unit sphere, and it's essentially as if you would measure the distance or the similarity between two nodes through the cosine similarity instead of the regular dot product or the end distance. Okay, so some words about the other type of graphs. As I said, there are many interesting cases, and practically interesting graphs that are bipartite. And so what can you do? Well, you may, so this is an example. Let's say on the left you have the users, on the right you have the products they have bought. And so you'd like to, again, embed the users and embed the products, and maybe embed them in the same space, so that you're able to identify users that are close or products that are close, or even a user that is close to a given product so that you may recommend this product, for instance. So you like to embed all these nodes in the same space, and obviously you can just forget the fact that this is bipartite graph. It's also a regular graph. Okay, you forget the fact that there are two parts, and you mix user and products, which is as if you just have applied the previous methods to this graph with adjacency matrix directly given by this bi-adjacency matrix, the bipartite graph. So this is quite easy. There's another things you can do which is a case of directed graphs, so it's a bit less obvious. There are many cases where you have directions. You may think of, I don't know, Twitter, where you may follow, I don't know, Emmanuel Macron, but maybe Emmanuel Macron is not interested in your business. Or you may think of the web graph or Wikipedia, where you have links between pages that have a direction. And unfortunately, you cannot apply directly what I mentioned about like the spectral decomposition of the Laplacian or the transition matrix. It simply does not work, and you may have a complex spectrum and so on. So what can you do? Well, you can represent this directed graph as a bipartite graph, simply by copying each node. So each node has two representations as a source of edge and as a destination of edge. Okay, so I don't know, maybe this node is that one. So you have two outgoing edges. So the degree here is 2, and you have one incoming edge here. So the incoming degree of its right representation is 1. Okay. And then you can apply, of course, the previous trick for bipartite graph. And so you have a co-embedding of each representation of the nodes. So here, the interpretation, I mean, as a source of edge and as a destination of edge really depends on the type of graph you consider. And you may simply forget one of them and, for instance, consider the representation as a source of edge. Some words on the algorithm. So you need to compute the top eigenvectors of a symmetric matrix, which may be the Laplacian. So if you have the transition matrix, it's not symmetric, but you can, I mean, make it symmetric and do the computation. There's a technical step to do that, but it's quite easy. So if your metric is not too large, meaning like, I don't know, less than 1 million edges, let's say, you can use Langsouth algorithm, which is based on, I mean, this idea of power iteration to get the top eigenvector. So actually, Langsouth algorithm is a way to obtain the first top k eigenvector simultaneously. So it's very efficient. Now you can do that for very large matrix, and in this case you may use Langsouth algorithm, which is much more recent actually, which is sometimes not very well known, but it's very efficient, and it uses a combination of random projection, power iteration, and QR decomposition to find relevant orthogonal basis of to what you can project your metrics, and then you apply essentially Langsouth algorithm to this metrics in a much lower dimensional space. So actually you can really apply these techniques to graphs having, I mean, hundreds of millions of edges, if not billions of edges. It really depends on the RAM. Can you store all your graph in RAM? But it's really very efficient, and many people claim that this spectral method do not scale, but it's wrong. I mean, it's really these are scalable methods. Just a comment on regularization. Maybe you have noted that if you do regularization, actually you make your adjacency matrix dense, which is not good news. If you have millions of nodes, you will not be able to store this matrix. But obviously, it's not a good way to do it. Actually, you will not store the dense matrix. You will remember that actually your matrix has a nice sparse plus low rank structure, which you may store this matrix this way. So essentially here you will store your original matrix A and this gamma factor. And as you can see, you can easily do this matrix vector multiplication. It's just AV plus gamma, the dot product of V with a vector of 1 multiplied by 1. Okay, so you can do it, and it's enough to apply this Langsos and Alcos algorithm to find the corresponding spectrum of the matrix. Okay, now some experiments to show you the impact of regularization, scaling, and normalization, and also the impact of the technique you may choose based on the Laplacian matrix or the transition matrix. So first you may consider Openflights. So these data sets are available here. So this is a set of a collection of networks or graph data set we maintain, which are available directly through scikit-network. I will show you this a bit later. So you can have a look at them. And so Openflight is a nice graph of all the flights between the top airports in the world. So there are 3,000 nodes corresponding to the airports, and more than 30,000 edges, so the daily flights between these airports. And this graph is weighted. So the weight is the number of daily flights between the airports. So for instance, between Paris and Tokyo. So I haven't mentioned that, but all the techniques I've described so far work for a weighted graph. Okay, you don't have to necessarily to assume that your adjacency matrix or biadjacency matrix is a binary. It can be any matrix with positive entries. So this will be the first data set. The second data set is a very nice data set we've built at Telecom, and it's a graph of links of let's say the 10,000 vital pages of Wikipedia. So in Wikipedia, there are people voting for the vital pages, the top pages of Wikipedia. So on many different topics, and so you can extract a subgraph of Wikipedia talking about these topics. And well, there is a page on graph theory in it. You have a page on artificial intelligence, and there is an edge from graph theory to artificial intelligence in Wikipedia. So it's a directed graph, which is much larger than the previous one. And then 10 labels, so the categories of the pages. Okay. So for the first data set, you may apply spectral embedding, and what we'll do is simply k-means. Okay, we'll try to see the 10 top clusters in the embedding space. So remember that you can't apply k-means on the original adjacency matrix. First you can't do that if you apply scikit-learn, for instance. I'm pretty sure you cannot put as an have as an input a sparse matrix. You need a dense matrix. I need to check, but I think so. And in any case, it would give I mean, some arbitrary results because of this problem of the curse of dimensionality. And so, but you can do that in the embedding space, of course. And so what we'll do is that you take your favorite embedding technique. So here I use the transition matrix of the random walk. Dimension of the embedding space is 10, and apply a regularization factor of 1%, meaning that the total weight of the regularization in the graph is 1% of the overall weight. Apply a scaling of 1/2, meaning that you equalize the levels of energy, and apply normalization. So all the vectors are on the unit sphere. Then you apply k-means, and this is what you get. So I haven't shown here the edges. There are too many of them, so only the nodes with their location in the world. And as you can see, it looks like these clusters make sense. I mean, they correspond to a region, I mean, homogeneous region of the world. And now the question is, well, just to visualize the impact of these different techniques, what would be the impact, for instance, of applying this to the Laplacian matrix instead of the transition matrix as I did here. Okay, and just to visualize the result. So this is what you have on the bottom of the slide. The top is the same as the one I've shown. And the bottom, you have the one you get with the Laplacian matrix. So first, as you can see, I mean, these results are very different. Okay, and probably the embedding you get is less interesting because it looks like most of the nodes are concentrated in some region of your 10-dimensional space because they are put in the same cluster by k-means. Okay, so maybe I mean, of course, you need more metric to assess this, but visually you can say that indeed probably your embedding is less interesting. It tells you less about the structure of the graph. About the regularization, well, again, so the top is a reference technique. On the bottom, you have the embedding with the transition matrix, but no regularization. So again, the system is different. So both looks interesting. It's hard to say what would be the best regularization. So maybe here, that's an open question actually. What would be a good parameter for that? If you have ideas, I'm very interested. But for sure, you get very different results with regularization. And there are cases where actually you can, which is not the case here because the graph is completely connected. You can go from any airport to any other. Maybe the impact of the regularization is less than for other graphs. This is the impact of scaling. Again, it's not so obvious the impact it has, but here is a very interesting result about normalization. If you don't normalize, if you don't put this vector on the unit sphere, then again you get something that looks much less interesting. Let's say 90% of the nodes turn out to be in the same cluster. For Wikivitals, so the subgraph of Wikipedia, so these are you have labels, ground truth labels. So you have very different topics of these pages of Wikipedia, and you can use them to compare with the labels found by k-means. Okay, and you have a usual metrics to assess the quality of your labeling or clustering, which are the adjusted round index and adjusted mutual information, so ARI and ANI. And this is what you get. So again, the top line is a reference embedding with the transition matrix. It turns out to have the best score for both metrics, and you see that the impact of the other, either the Laplacian you choose or the different post or pre-processing technique is significant. You have a significant impact on that. This is just a representation of this embedding in 2D with the actual 10 clusters with the ground truth labels. Okay, so this is a summary, at least for the first part. I will try to be very short, shorter for the next part. So spectral method for graph embedding. So these are scalable methods through random projection, and many people, are not aware of that. They are explainable through physics, and that's very interesting when you compare to other embedding techniques like those based on neural nets. Okay, they are really, you can talk about energy. This is a property of Barycenter. There are many things you can do and write mathematically, which is quite nice. It's applicable to all types of graphs, like bipartite and directed graphs. And also, again, many people think this is restricted to the undirected graph. And it's also very sensitive to the type of pre-processing and post-processing technique you may apply. And in particular, we have tried to put in scikit-network the default parameters that give you a good embedding in most cases. So maybe before I move to scikit-network, I may take some questions you may have. So it may be either on the chat or you may, I don't know if you can, you can talk, I guess. So well, otherwise I can, yeah, so how you solve the optimization problem. So the optimization problem is a trace, a very nice problem because it's a trace problem with nice constraint, and you can really show that it's given by the spectral decomposition of the matrix you have on the trace. Okay, so really maybe I've not been very clear on that, but if you look at this, no, maybe you should, yeah. If you look at this trace problem, which is the optimization problem, the solution is directly given by the top eigenvectors of your matrix. You can write it quite easily. It's a standard problem. So I hope it answers your question. Okay.
Thomas, je ne peux pas lever la main, moi, mais je crois que Maclouf lève la main, là, je vois.
OK. Eh ben, je l'écoute. Est-ce qu'il peut prendre, je pense qu'il peut parler.
Oui, je préfère, si vous m'entendez.
Oui.
Ouais, très bien. Comme j'ai plusieurs questions, je préfère parler directement pour
Bien sûr.
économiser un peu le temps. Je voulais d'abord te remercier pour ta belle présentation. Je suis un peu confus en fait entre le titre de la présentation sur l'embedding of graphs versus, peut-être que tu vas m'éclairer davantage, sur ce qui se fait en fait dans l'embedding des graphes, notamment des graphes virtuels, donc dans les réseaux virtuels. Je m'attendais en fait à un petit peu ce sujet-là, mais je suis un petit peu bluffé entre guillemets. Vois-tu un lien entre la notion d'embedding à travers notamment les méthodes spectrales que tu exposes, avec ce qui se fait dans l'embedding des graphes dans les réseaux virtuels, notamment, je fais notamment un lien, référence au problème du VNI, que tu connais certainement, le Virtual Network Embedding, où on essaie en fait de trouver une espèce d'isomorphisme de graphe sur un autre graphe. Donc ça, c'est ma première question.
Donc les réseaux virtuels dont tu parles, il s'agit de quoi en fait?
En fait, si on cherche, mathématiquement parlant, ça revient à chercher à trouver un isomorphisme de graphe partant d'un autre graphe. En fait, on cherche à trouver son isomorphisme sur un autre graphe plus large.
D'accord. Je ne connais pas de technique effectivement qui utilise ça. Je n'ai pas cité. Il y a peut-être un lien, mais en tout cas, là, en input, on a un seul graphe, on n'a pas deux graphes, ça c'est sûr.
Ouais, ok. Et du coup, si je reste sur un petit peu l'approche que tu exposes, est-ce que tu as des contraintes sur le domaine dans lequel tu projettes ton graphe?
Là oui, c'est vraiment un espace euclidien standard, quoi.
D'accord. Donc,
après, on peut on peut faire du post-processing pour mettre ça sur une sphère ou je ne sais pas quoi. Mais là, effectivement, c'est un vecteur, c'est la vectorisation de graphe. C'est vraiment, on ne met pas de contraintes. Enfin, on met une contrainte, les contraintes que j'ai exposées en termes de covariance, etc. C'est une contrainte, pas sur l'espace, mais sur le type d'embedding qu'on va obtenir. On veut bien couvrir l'espace, etc. Il n'y a pas de contrainte sur l'espace lui-même. On ne peut pas mettre ça sur une variété ou je ne sais pas quoi.
D'accord. Dernière question et je libère la parole. Est-ce que tu as certainement regardé ça? Tu parles d'embedding des nœuds. Et est-ce qu'il y a aussi le problème d'embedding des arêtes ou des arcs éventuellement quand on est sur des graphes orientés? Est-ce qu'on est sur des mêmes approches
Alors, ça, c'est une excellente question. C'est vrai qu'on ne l'a pas fait. Il y a des choses qui existent. C'est beaucoup plus… alors, du coup, ça ne passe pas trop à l'échelle, quoi.
Ouais.
Donc, c'est la raison pour laquelle bon, on n'a pas trop regardé ça. Mais bon, la question est intéressante. Enfin, en fait, ce qui existe, c'est plutôt, une fois qu'on a fait l'embedding des nœuds, on peut évidemment repluguer les arêtes dans l'embedding et puis faire du traitement là-dessus.
Ouais.
Mais faire de l'embedding directement d'arêtes, je ne connais pas de technique qui marche sur des grands graphes.
Je te remercie.
Ouais.
C'est tout pour moi.
C'est peut-être plus facile avec les réseaux de neurones. Je pense que des gens font ça avec des réseaux de neurones. Parce qu'évidemment, on peut aller chercher des couches cachées au milieu qui correspondent soit à des nœuds, soit à des arêtes. Et donc, on pourrait faire ça avec des réseaux neuronaux, j'imagine.
D'accord. Il y a un petit mot rapidement sur la complexité des approches là que tu cites, même si tu dis que c'est scalable.
Eh ben, en fait, c'est la complexité du solver, qui sont hyper optimisés, par exemple dans SciPy, qui est, et donc, bon, ça va dépendre évidemment du nombre de vecteurs propres qu'on demande.
Ouais.
Mais voilà, nous, on fait tourner ça sur des graphes à des centaines de millions d'arêtes, quoi. Avec si tu cherches une dimension 10, si tu cherches une dimension 100 ou 200, ça va te prendre plus de temps, mais en tout cas, tu vas finir par avoir le résultat, quoi.
Okay.
Pour des gros graphes. Mais sur des petites dimensions de l'ordre d'une dizaine, avec toutes les choses raisonnables, c'est immédiat. Enfin, c'est sans comparaison avec les techniques basées sur les réseaux de neurones.
Ok. Je te remercie beaucoup.
De rien.
J'avais une toute petite question vraiment sur l'application présentée sur Openflights.
Ouais.
Les arcs sont pondérés par quoi? Par le nombre de vols réalisés par semaine? C'est ça que j'ai cru
Par
comprendre.
jour, ouais. Enfin, par jour, par semaine, mais oui, c'est ça.
Oui, d'accord.
Évidemment, ça date pas, c'est pré-Covid tout ça.
Oui, bien sûr. Ouais. Je sentais mais par contre, c'est pas pondéré par la distance. Ça aurait pu être pondéré par la distance entre
Non, pas du tout. Et justement, en fait, c'est les liens, les poids qu'on met sur les arêtes, on les interprète comme la force en fait entre les liens entre les nœuds. Et deux aéroports en quelque sorte qui ont beaucoup de vols et retours entre eux sont plus forts, quoi. Parce que vraiment, si on regarde l'interprétation physique, on interprète les poids comme des forces, des ressorts. Et donc, plus le poids est important, plus on a envie que les nœuds soient proches. C'est une notion de similarité. Ou pareil, dans les graphes bipartis, si un utilisateur a acheté 10 fois le même produit, et il va avoir un poids plus fort, une distance plus faible en quelque sorte vers ce produit que s'il a acheté un autre produit une seule fois.
May I also ask a question?
Yeah.
First of all, thanks a lot for the great talk and for presenting in English. It really helped my understanding. Do you have an intuition what happens to the eigenvalues when you regularize? I mean, is there a mapping of the unregularized eigenvalues to the regularized eigenvalues? Is there some shrinkage of the spectrum which is going on, and if so, towards what center are the eigenvalues shrinked?
That's an excellent question, actually. And there are works on that. So, of course, if you have a very small regularization parameter, but to be honest, I don't have this result in mind. But I'm not sure it's very explicit, actually.
Because obviously,
I'm not sure you have a clear mapping between the spectrum of the. Actually, I even think that it's not continuous. I mean, if in some, it's related to the work we've done with Nathan. We have shown a very simple case, which is a block matrix, so a block model. We can show that actually in these particular graphs, you don't have continuity in zero. So if you have very different result, if your regularization parameter is 0, or if it's any epsilon. If it's any epsilon, you will be able to recover the top blocks, the top eigenvector. It's not guaranteed if it's 0. It's more or less random. And so, well, you may have to impose some assumption on your graph to be able to have continuity in this gamma and to have some more or less expression of the of the spectrum of the regularized system. But it's a very interesting question.
Thanks a lot.
Yes.
Bonjour, oui, j'ai une question. Je m'appelle Lucas Castelli et j'ai travaillé au LIX à Polytechnique. En fait, c'est très joli le résultat que vous avez montré sur les dessins spectral, disons, vous l'appelez plongement spectral pour le cas du réseau des vols. C'est vraiment impressionnant la capacité de l'algorithme de reconnaître les clusters, tenant compte des contraintes géographiques. Je me demandais, d'un côté, est-ce que vous avez essayé d'autres jeux de données, d'autres réseaux qui ont des contraintes géographiques? Je pense qu'en littérature, il y en a quelques-uns. Et aussi, deuxième question, est-ce que vous avez comparé avec d'autres algos de clustering, pas du tout le spectral, par exemple les hiérarchiques ou les
oui, bah donc je voulais en parler. Merci, oui, bah merci pour la question. Enfin, donc pour la première question, là dans notre jeu de données standard, notre terrain de jeu, c'est on n'a que Openflights qui soit géolocalisé, mais on a des données qui sont pour le coup pas publiques sur par exemple des transactions bancaires ou des choses comme ça. On a aussi la géolocalisation et on peut effectivement retrouver des caractéristiques géographiques directement à partir du graphe. Sans évidemment là dans les résultats que je vous ai montrés, l'algorithme n'a pas du tout les positions GPS et c'est juste pour il retrouve en quelque sorte ces contraintes géographiques avec des algos standards. Donc il y a effectivement plein de données géographiques, des données publiques dont on dispose et qu'on met à disposition. Il n'y a que celles sur Openflight. Là. Sur la deuxième question, oui, on peut comparer. En fait, je vais vous montrer la scikit-network si j'ai peu de temps. On a vraiment tout plein d'algos disponibles. Et en ce qui concerne le clustering, en général, il y a un très très bon compétiteur qui est l'algorithme de Louvain. D'ailleurs, je vais vous montrer tout à l'heure ce que ça donne, qui est un algorithme pur graphe. Donc, il n'y a pas besoin de passer par une représentation sur un espace de faible dimension. Et c'est vraiment connu comme étant un des algos centraux des graphes, enfin vraiment qui marche hyper robuste et qui a très peu de paramètres. Là, il y a quand même quelques paramètres que j'ai mentionnés. Le premier paramètre, c'est quand même la taille de l'espace, la dimension, et puis il y a éventuellement la régularisation dont on a parlé, et puis le scaling. Donc ça fait quand même des paramètres à régler. Avec Louvain, il n'y a essentiellement pas de paramètres. Un éventuellement si on veut regarder la résolution, mais même l'algorithme de base marche très très bien. Donc, et il y en a d'autres, il y a d'autres algorithmes qu'on essaye de mettre dans scikit-network.
Sans vouloir te presser, je pense qu'il faudrait peut-être que tu passes à tes dernières
slides.
Oui,
je vais. D'accord. Ouais. Donc, ça va aller plus vite. Hein, je vais. Donc, on a jusqu'à 15h30 ou c'est ça? Ou c'était 15h? Patrice, c'était 15h30, c'est ça qui était noté?
Oui, c'était 15h30. C'est la fourchette la plus large.
D'accord. Je vais aller vite. Voilà. Donc, quelques mots sur scikit-network. Donc, comme je l'ai dit, c'est une bibliothèque Python qui est inspirée de scikit-learn, mais qui a sa vie propre. Après, la question de savoir si ça doit intégrer, si ça peut ou si ça a vocation à être intégré à scikit-learn, c'est une autre question. La grosse différence avec scikit-learn, c'est qu'on prend en entrée des données qui sont sparses, donc des matrices creuses. Ce que fait scikit-learn parfois, mais la plupart du temps, non. Et donc, on a notamment des algos qui sont purs graphes, ce que n'a pas scikit-learn. Mais dans la philosophie, l'usage, etc., c'est vraiment très proche de scikit-learn. Toute proportion gardée, évidemment, quand on voit le succès de scikit-learn, on est quand même des petits poussés. Pas question de se comparer à scikit-learn, mais c'est juste dans la philosophie, dans l'approche qu'on a été très inspiré par scikit-learn. Donc, c'est facile à installer, c'est une ligne en pip install, c'est facile à utiliser, donc c'est la même API. I should switch to English, sorry. It's the same API as scikit-learn, so the algorithm are objects and you feed them to data. it's documented, it's very fast, and so on. And it's relies only on two, there are two dependency, NumPy and SciPy, which are regular package in Python. So the data format, as I say, graphs are represented as by their adjacency or bipartite matrix, which are sparse metrics, and we use the standard CSR format for those who know of SciPy. Okay, and this allows us to do very fast matrix vector products and to be very efficient for most algorithms. And so we use also Cyton, so I won't enter into details, but for some algorithms like Louvain, which are algorithms, we use Cyton, which is a C extension of Python, where you have to type variables, and it's completely transparent to the user. You don't see that it's not Python. You can have a look at the code as well, and but it's very efficient for this algorithm. So I will skip that, but of course we have competitors, and the most famous is NetworkX, which is in Python. But so to make a long story short, NetworkX is not scalable at all, mainly because of the way the data format is chosen and the way data is represented. For instance, if you like to work on a classical graph, which is Orchid graph, so it's a social network. So it's not a huge graph, but it's reasonable with millions of nodes and 100 millions of edges. Well, you can't do that in NetworkX. And if you look at the RAM usage compared to our competitor that are in C, we have a much more efficient, representation of data. It's only 1 giga, whereas you have 18 giga for iGraph. And it's really, it's not us, it's just the fact that the CSR format of SciPy is optimized, and this is the choice we've made. In terms of running time, it's very fast. It's comparable to the package that are used that are coded in C, and in some cases it's much more efficient, like in Louvain. So maybe we'll have in a couple of minutes I can show you. I hope. Yeah, you can see the, tell me if you don't see, you're supposed to see the package here. If it's not the case, so please tell me.
No,
so,
you don't see it.
You don't see it? Okay, so I should stop the sharing, and I will share quickly the other, yeah, that one. Now it should work. Can you confirm?
Yes, it's okay.
Okay, so this is the documentation of our package. So you have the reference where you can see, the complete documentation. I don't know if you like to. I've talked about embedding. So embedding is here. You have the spectral embedding, and this is, for instance, the embedding with the parameter I've talked about, like regularization, the number of components, and so on. Okay, and so if you have to get more detail on that, you have access to the code in Python. Plus, you have tutorials like if you'd like to start, you have some easy way to start with your favorite graph, maybe NumPy, or from a list of edges, or from if you use NetworkX, you can import a NetworkX object and export in CSR format and use scikit-network. Okay, so well, for instance, regarding embedding, it explains you how to embed your data, and for instance, to embed a graph, you have this spectral method, and you fit it on the data, or here you fit transform, since you want to get directly the embedding on the adjacency matrix. And this is exactly the same API as a scikit-network. Maybe if time permits, can show you a notebook, which is a way to how do you cluster Wikipedia vitals, to show you a bit how it works. So these are the methods or objects you need to import. Essentially, you need to load data cluster. They will briefly show you how to do hierarchical clustering. And you may want to rank nodes and visualize results. Okay, so loading the data is just one line of code, and you can have a look at what you have loaded, and it's just a dictionary, and this dictionary is composed of you may have a look, like metadata tells you that these are the vital articles of Wikipedia. You can extract the adjacency, and as I say, the adjacency matrix is a SciPy object, so it's a sparse matrix. And these are the names of the pages and so on, and you can have a look at this. This is a list of the names of the 10,000 pages of Wikipedia. So you can apply Louvain, and so it's just a fit on the adjacency. Look at the labels. You have 7 of them, and this is a representation of the aggregated graph. So you have 7 clusters, and these numbers are the number of original nodes in each of these clusters. Okay, you may have a look at what is in each of these clusters. What are the top pages of each cluster? You may use PageRank for those who know. And for instance, you see that the first, the largest cluster talks about biology. The second one is on mathematics and physics, and yet then you have something on geography and so on. Okay, and this is the corresponding graph. Now you may want to know what happens inside one of these clusters. Let's say maybe the one on topology, on biology, and this is quite interesting since if you like to get this subgraph, so what is inside this set of nodes, you can just do some slicing. So what is nice is that you manipulate regular SciPy objects, so sparse matrix, and so you can use the slicing to get the corresponding adjacency matrix of the cluster you look at. And then you still apply Louvain, and you see some subclusters on these big clusters on biology, and you see that this talks about plants, these are bacteria, and diseases, and so on. And finally, you can do that automatically. So try to have a look at each of the sub-clustering of these big clusters and do this at several levels. And this is what you would refer to as a hierarchical clustering. And so here we use a Louvain hierarchy, but there are all other methods. And if you apply this, you get a tree. And so these are the top 7 clusters. And these are, for instance, the first subcluster we've seen for the biology cluster. But you may see that there are other subclusters on different topics. Okay, so it's just to show you that if you like to import this graph, so that we have in our collection, it's just one line of code, and you can start playing, and it should be quite user-friendly. If not, I mean, please inform us, or you're welcome to contribute to the package. I hope it was not too long. So if you have any question on this, so I see that Makluf has a question. Feel free to ask.
Yeah, thank you, Tom. A quick question. It's about the anomaly detection. You already mentioned at the beginning of your slides. How could you, could you tell us in few words, how can we use this tool for maybe for fraud detection, for example?
Well, this is something we've not done yet. And usually when you think of fraud detection, I mean, the typical way you do it, I'm aware of, use patterns. You try to look at some patterns, like if you think of illicit, flows of money or so on, you may try to find some patterns you may have identified, and then you try to have a look at those patterns in the graph you have. And this is something we've not done yet. So if you have, we are open to write a module on that, and but this is not something we've not done yet. About anomaly detection in general, if you like to identify, like edges that are that look weird or nodes that look weird, you may use usually a usual anomaly detection technique in the embedding space. I'm not really aware on techniques working directly on the graph, but there may be some. So to be honest, we've not worked too much about this problem of anomaly detection, but for sure you may apply this in the embedding space.
Okay, if I can suggest just one very interesting publication in this field, maybe that can interest you. The name of the title of the paper is Fraudar. It's about, as you talked about, credit card, for fraud detection issues. So you can take a look. This is really an interesting paper. It's from Carnegie Mellon University. So I can send it to you if necessary.
I will have a look.
All right, thank you.
So I see that there's something on the chat. Yes, so I guess the slides will be made available. Okay, I guess on the website of SystemX, on the seminar.
Oui, exactement. Il y aura une mise en partage, une mise en ligne.
Est-ce qu'il y a d'autres questions? Sinon, je voudrais remercier tout le monde.
Moi, j'avais juste, avant que tu conclues, je voulais juste te montrer un petit. Alors, c'est vraiment un petit clin d'œil. Je vais partager autre chose à l'écran.
Ouais, je vais arrêter le partage.
Non, ça va l'arrêter, je crois. Je voulais savoir si tu avais quelque chose à voir avec ce graphe.
Alors, c'est effectivement, donc ça, c'est un graphe qui est fait, si je ne m'abuse, par Olix. Donc, Olix, je ne l'ai pas mentionné, c'est aussi une de mes affiliations.
C'est ça, c'est parfait.
Laboratoire commun, d'ailleurs, SystemX et Télécom Paris, Inria, Nokia, et j'en oublie au moins Paris 6. Mais effectivement, il y a des collègues qui utilisent des graphes pour représenter un peu les membres de ce laboratoire. Et donc, je suis en…
Des liens, c'est des liens à travers les publications communes, c'est ça, non?
Exactement. Donc, c'est tout à fait ça. Et le positionnement, etc., utilise évidemment ça. Donc, c'est une forme d'embedding en 2D du graphe, tout à fait. Ouais.
Est-ce que ça a utilisé scikit-network
Non, parce que c'est un truc qui a été développé en parallèle depuis un moment. Donc, on est évidemment, on travaille sur les mêmes sujets, on travaille ensemble, mais ça n'a pas utilisé directement scikit-network. Ça a été fait plus pour faire de la visualisation sur des petits graphes, donc c'est pas tout à fait la même cible que scikit-network.
Très bien. Ben, je voulais conclure en te remerciant encore de tes éclairages. Je pense que ça pourra faire naître peut-être des idées de collaboration et de projets avec ou sans SystemX d'ailleurs, mais enfin, je crois qu'il y a dans les 50 personnes qui étaient connectées une majorité de SystemX, mais il y avait beaucoup de gens aussi externes. Et donc, je voulais remercier tout le monde d'avoir été connectés. Nous, côté de notre bâtiment Digiteo, on a eu un petit souci à la fin de la présentation parce que le réseau est tombé, électricité aussi. Donc là, je suis sur batterie avec mon téléphone portable.
Ah oui.
Mais voilà, hormis ce petit souci technique, je pense que les autres étaient bien connectés. Merci encore, Thomas.
Merci à vous, merci pour l'invitation et l'opportunité de présenter tout ça. Et puis, s'il y a des gens qui sont intrigués ou intéressés par scikit-network d'une manière ou d'une autre, évidemment, on est là pour répondre à vos questions.
Merci encore et au revoir. Bonne fin de journée à tous.
Merci.